I'm Sandeep Nair, and I'm going to be discussing how we can build RAG applications using Cosmos DB NoSQL API. How can you use Cosmos DB and OpenAI? So I wanted to know, how do you use Cosmos DB and OpenAI together? So one, of course, you can, and again, since this is all about AI, I didn't want to create my own slides. I just asked OpenAI, ChatGPT or Bing here to give me the answer. So these are the different scenarios in which Cosmos DB and OpenAI can be used. The one could be where you can build a chatbot or any kind of bot by interacting with it. Two, you can use the vector indexing feature for other use cases. Three, you can use it for chat history and storing history, etc. So there are multiple scenarios in which Cosmos DB can be used with OpenAI. And in this current demonstration that I'm going to do, we are going to focus on the first one, which is to say, how do you build a chatbot, or how do you interact with OpenAI, like using a chat interface. So next question, what is RAG pattern? So again, this is the response that I got from the ChatGPT. And when you say RAG pattern basically breaks it into retrieval, augmented, and generation. So I like the second bullet very much, where it says the RAG model has got two components. The first component is that you have a large corpus of text and you need to find relevant document, the keyword there being the relevant word. And second thing is the generator, is that you use the documents that you retrieved and then use the OpenAI capability to generate a response, right? Now, with these two pieces of information, and let's read the first bullet once again. Think of you being asked to write an article on a subject that you don't know. What are the kind of things that you do? Your first thing is to go and do a lot of research, go and figure out all the relevant information. Two, then you take that data and then start doing some creative writing around it and write a story. So what RAG pattern is exactly like that. It first goes and gets the data. And once the data is available, it uses that data and generates a response based on the user's query. So that's basically RAG pattern in a very basic concept, layman's term. This is not the technical answer to it, but we'll come to technical answer for later. But I just want everybody to understand this concept. So let's study how does RAG actually work in our technical space in an application. So this is how we used to build simple applications or applications before the Gen AI boom happened, right? So you had a user who would provide input in a structured input. So when I say a structured input, I meant some kind of console. It could be a web form, it could be a mobile interface, it could be a command line, it could be providing data in a JSON structure, XML structure. But whichever way you look at it, the data was supplied to the system in a structured way. Now, you would write your business algorithm, which would know what the structured inputs are. It would read that structured input. It would query the database, typically using SQL or something equivalent. And the database would return a data set. And then that data would again be converted into a structured output and presented as a report. Again, a report can be a dashboard, a report can be a web form, a report can be a PDF, a report can be a web page. So reports can be of various kinds, but again, the output is structured. So what was the key part here is that all this interaction required data to be structured, which basically meant as human beings, we required to adhere to some structure that the application developer had come up with. So you had to learn how to get to align to the structure. So that is how applications were working earlier. And now with AI, what changed? What changed is that the structure went away. Now user is interacting with the system in natural language. Natural language basically could be English, could be any other language. So you are asking the system in just like you would ask your friend, your colleague, or somebody else on the street. You are interacting with the system in natural language. Now, when you interact with the system in natural language, your intent, your question has now to be used and the data in the database has to be fetched. And that's one place where, we as Cosmos DB team have a role to play, and that's called the vector search. So basically, when we say vector search, what we are talking about is given an object, find similar objects. Now, this object can be anything. An object can be a file, an object can be a piece of text, an object can be a graphic, an object can be an MP4, an object can be any digital asset. So now, so what we do is you take a reference object and then say for this reference object, what are the objects in my database which are similar? Or so now using the correct keywords here, the object that we talk about is called a vector, or it's also called an embedding. And then this search is called a vector search, and the search type is called similar closest neighbor search. You're trying to find the closest neighbor. So similarity, you're looking similarity score, right? So what happens in the new world is the user provided an input, let's say in English. And let's say the user asked a keyword like, what is the stock price for Microsoft share? Now, this sentence has to be searched in my database. So the first thing that I need to do is I need to convert this text into vector. Now, how do I convert it into a vector? I will use an embedding API to do it. There are many APIs. OpenAI provides some APIs. There are APIs from Hugging Face and other providers also. So you take the text and you vectorize it. Then with that vector, you go and search it in the database. Now, when I say the database, these databases can, so if you see there's a blue dot around the database, the reason why I have shown them as two separate objects is they can be two separate databases. They can also be the same database. So it is up to, so some databases, for example, let's say you are a legacy application built on, let's say, SQL Server on-premise, and you do not plan to move that database completely to the web or to the cloud. So then how do I do a vector database? So in that case, you can have a vector database, which is only doing vector search on the cloud, but you can then do the rest of the stuff on your existing database one way. Second method, okay, my application is already on the cloud. I'm already using Cosmos DB NoSQL or Cosmos DB MongoDB vCore. In that case, I don't require two separate databases. I can use the same database and do it. So here, essentially what you're doing is you will run a query, and the query will, along with just like any other query operators, you also have a similarity score or a vector distance function, and that will return you the objects, and then you'll sort it and you'll say, okay, I want top 10, top 15 objects from it. And then I will take that data, the data that was retrieved from the database. I will give that data to the LLM, which for example, let's say an OpenAI ChatGPT, and I will also give the ChatGPT some instructions, and that's called prompt engineering. And these instructions are again in English. I am just telling the LLM how to behave. So basically, it's more like the rules of engagement. And third, I am giving the LLM the input that the user had made in native language as is. So remember, the user input, which was in native language, is coming to the LLM in two forms. Form number one, it is getting converted to a vector. And then the vector is getting used to do a vector search in the database, and the search results are reaching the LLM. Also, the natural language input that the user provided in its raw form, exactly same sentence as the user asked, that is also provided to the LLM. Now, the LLM takes these three pieces of information: the prompt, the data retrieved from the database, and the natural input from the user, and it generates a response. And this response is again called completion. The reason why it is called completion is because, again, it is in natural language. If you ask it in English, it will return it. It can return it in English. But if the prompt said that I want a JSON file out of it, then the LLM will generate a JSON file out of it. Or if you say generate a CSV out of it, the LLM will generate a CSV out of it. So depending on what your instructions are, the completion can be in different format, but it can be in natural language also. So this is how RAG pattern works. And what I'm going to do now next is to show you the capabilities in Cosmos DB NoSQL. So what does Cosmos DB have? So Cosmos DB NoSQL API introduced vector search last month. And basically, it provides you three ways to do your vector search. The first method is called the flat search. The second one is called quantized flat. And the third one is called the disk ANN. So when you say, and all of these methods use the closest neighbor only. So, but the difference is which one to use depending on amount of data. So when you say flat, what it does is it takes your vectors, stores it as it is, and does a search. When you say quantized flat, it basically quantizes it. Quantization is like compressing it. So if you give it a big vector, it will reduce its size in some form, and it will try to not lose any data. So it will try to maintain the accuracy. And the third one is, okay, I have lots of embeddings, so I cannot store it in my index. So I need a large disk to store it. So then in that case, you use disk ANN. So if your data size is small, 50,000 records or less, you can go with flat and quantized flat. And if you have more than that, we typically recommend you to use disk ANN as a vector search method, or how to store the vectors, right? Now, once you do the vectors, how store the vectors, first thing, okay, you have to, if you have to use it in Cosmos DB, it's a preview feature, so you need to enable it using these steps. Also, disk ANN is right now in gated preview, so you will have to fill up a form and get it approved from the PG team. But once, and this is how you can actually, this is the command to enable vector search if you want to do it through command line. Now, once you, let's say you have got this feature enabled, there are two things that you need to do to be able to start using it. One, you have to create a vector policy on the container. Basically, vector policy tells you which are the paths where you are storing vectors. What data type are you using for a vector? Like I said, the vectors can be float, int, unsigned int, etc. What is the distance function that you're going to use? So you can use the different functions that can be used to calculate that distance. And what is the size of your embedding? How many dimensions are there? So depending on which service you are using to generate your vector, you will be able to identify the data type and the dimension. The distance function, you may have to do a couple of iterations and see which distance function is giving you the best result. So after doing a few iterations, you will be able to get it right. So similarly, if there are two paths, there, let's say a document has got two vectors in it, then this is how you can do it. And for example, if you see here, this one is using a float 32 and a 1536 dimension, which basically means this is a largish embedding because it's using float 32 as data type, and it also has 1536 items in each array, whereas this is an int 8 and just 100 dimensions. So this is a smaller embedding. And so here we are able to use dot product, and here we are able to use cosine. So again, this are some things that you will have to try out, study the embedding model and see which one is the best for you. But for every embedding that you want to store in your database, in your documents, you have to create one item in the vector policy. Once the vector policy is done, next is the indexing policy. So this is telling you what is the definition of your vector. And as you would see here, every path has got only one item, and it is defining the data type and the distance function. The next is the indexing policy. Now, indexing policy we already had. So this is an extension to the regular Cosmos DB indexing policy. And here we are going to tell, okay, given that vector, how do you want to index it? How do you want to use it? So these are the three types that we talked about: flat, quantized flat, and disk KNN. So there are some limitations here. So you can use only flat if you are having up to 500 dimensions. So the 1536 dimension item that we saw earlier cannot be stored here. The quantized flat can store it. And the disk KNN can store the bigger one, which is the 4096 dimension items. So depending on your vector type, depending on the amount of vectors that you're going to have, you have to use an indexing policy that is most appropriate for it. How do you write a vector index? This is how you do it. You say which path you are going to index it, and you have to say what is the type of indexing policy you are going to use. So in this case, it's going to use quantized flat. If there are two, you can use vector 1, quantized flat, vector 2, disk KNN. So this is how you would define it. So now, after this, your Cosmos DB is now ready to store any vectors, and you are ready to and it is also ready to index it. Now comes, how do I use it? So this is the NoSQL query, and what has a new function that has been added is called the vector distance. That's what is going to give us the similarity score. So what is the vector distance function do? First, it says what field I am going to operate on. So I'm looking for, I want to find the distance between this vector, which is 1, 2, 3, a three-dimensional unsigned integer array, and the field in my document, which is called content vector. When I run this function, it is going to give me a number between 0 and 1, and which is going to give me the similarity score. 0 basically means less similar, 1 basically means high similarity. So it is like a percentage point of how similar they are. So if, for example, c.content vector also had 1, 2, 3 in it, and here also it was 1, 2, 3, it will give you a 1, complete one. But very possible that if your content vector had 1, 2, 0, and you did a 1, 2, 3, your similarity score may be 6.6, 0.7, something like that. So you can do this, but again, this is a very simple representation of a vector. A vector typically has got much more number of dimensions. This is just to show you a very simple sample. So all that you now do is you can use the vector distance function and find the distance between the objects. And then you can, for example, if you see here, order by vector distance. And if you put a top also, then you can get the top items. So by doing this, you can say, get me the 5 items from, let's say, a product catalog, which are similar to the picture that I'm showing you. So using the picture, generate a vector, then using that vector, come to your Cosmos DB and do a search on the vectors of the products, and you will get the vector distance of all the products from the reference vector that you provided. And since you have done a top 5, it will give you only the top 5 items. And then you can show the customer that these are the 5 items that look most similar to what you have. So this is what vector distance is. Now I will show you how this whole concept that I explained can be used in a real life application. And so let's look at an application and see how it performs. So I have a small application here. It's called the recipe, Cosmos recipes application. We have the same application available in various flavors. This can also run in Mongo, vCore. But today I'm going to show you the NoSQL version of this. So let's look at it step by step. So as at this point, this application is connecting to Cosmos DB and getting you, making sure that everything is good. So you should see the status very soon. Okay. So Cosmos DB, the application has gone to the database and it tells me that there are no documents in the database. So let's go to Cosmos DB and see how exactly my database looks. So if you see here, this is the database and this is the collection that I am working with. If I come to scales and settings here, you can see that there is a container vector policy. This is the one that I talked about. So I'm using float 32 data type. I am using 1536 and I'm using cosine as here. And I'm using OpenAI embedding service to generate my embeddings. Similarly, in the indexing policy, I'm using quantized flat and there will be a document type. There's a document field called vectors. That is what I want the system to embed, index. So rest of the stuff is same. These are the two new tabs that got added because I have added the vector search preview feature to my account. So at this time, my collection is empty. There is no data. And next, what I want to do is I can upload some data. I'm going to skip option number 1. So if I don't have a collection, I had also an option in the code to go and create the container and build it as per my requirement. But since I've already done that, I'm going to skip to the next step, which is to upload the data to Cosmos DB. Now, this step is very simple. It is just taking some JSON files from my disk and uploading them to Cosmos DB. There is no special stuff. It is a simple insert operation that is being done. So let me just refresh this and show you the documents. So I can see that I have added some 13 documents. These are some recipes that I had prepared in JSON format. And as you see, they are very simple JSON files, nothing complicated, nothing specific on vector search being done, just some documents created in Cosmos DB. So now is the step, which is where we are saying we are going to vectorize it and store it in Cosmos DB. So in this step, there are two things that are going to happen. Step number 1, I'm going to take the document that's there in Cosmos DB. I'm going to send that document to the embedding API from OpenAI, and the embedding API is going to convert it into an embedding or a vector and return me. And then I'm going to take that vector and do an upsert of my document so that my document now also has got the embedding in it. So let's get started. So as you see, it's going to do it one by one. It's picking one document, getting the embedding, and then uploading it to Cosmos DB. And so let's go here and see what changed in the documents. So here, if you see, this is what the vector. So if you see this part, line number 5 onwards, this is the embedding that OpenAI generated. And remember, I told you my embedding is floating point. So you can see that it's floating point. And here, if you go from line number 1 to the end, you will see that there are 1536 items here. So it starts from line number 5, going all the way to 1571. Going all the way till 1541 here. So if you subtract 1541 minus 5, it is 1536. So there are 1536 items in this embedding. So depending on the embedding model that you use, your dimensions and your data type will be governed by that. I am using OpenAI embedding model here. And that's why I'm getting this one. And again, OpenAI also now has got different embedding models. I'm using the ADA 003 model. So that's what is generating this 1536 floating point embedding. So now part 2, I have the original document that I had, but I have also updated it with what I'm calling vectors, which is the embeddings. Now this embedding is a representation of my document. How? I don't know. That is what OpenAI model does. But the idea here is that if I were to give a reference vector and say, find me similar items, then this embedding will be compared with the reference vector. And based on the cosine distance, because that's what my vector policy says. It will find me the items which are close to the reference vector. That's the whole idea. So now I have my data, and now I can use OpenAI and start interacting with my data. So here in this case, I have 13 documents and they're small documents, and I can send all 13 documents to OpenAI. And when if I give it those data and ask a question, OpenAI is going to be happy to answer my question. However, in a real enterprise application, you are not dealing with 13 documents. You're dealing with maybe terabytes of data. Now, how do you find from your terabyte of data what is the most relevant documents? If you remember, I emphasized on the word relevant when I was presenting the PPT or for the RAG pattern. The most important part is finding the relevant data, because you cannot submit all your documents, terabytes of data, to OpenAI for it to interact with you. OpenAI expects that you will provide it some data. The amount of data is defined by the number of tokens that you have. So depending on the model that you're using, you will have a limit on the number of tokens that you can use. And if you provided lots of data, you're consuming all your tokens, and then the system will throttle and it will not function. So you have to work with limited amount of data for each call of OpenAI. And vector search, because of the similarity search, can give you a good tool to restrict the data from your database, which is similar to what you're looking for. So this is just a mechanism of restricting data that you send to OpenAI. You do not always have to use vector search for doing this. If you can do it using regular queries, you can very well do that. But if I am going to interact with the system in natural language, converting my natural language question into a normal query takes effort and it is not always accurate. That is why vector search is a good tool when you're dealing with natural language. If you're not dealing with natural language, if you have a very structured way of taking input, then you really don't need vector search for doing the or to find the relevant documents. You can use regular queries to do it and proceed with the same approach. So I want to emphasize here, vector search is not a replacement for regular queries. Vector search is an addition to regular queries where you either have to interact with the natural language question or you are searching based on another vector. For example, find me objects which are similar to the graphic shown. Now, you cannot convert a graphic to a query. So you convert the graphic to a vector and then you use it. So if you have seen all the ads that are coming today lately on TV, which is where you can circle something on a phone and it will go and search and get you the results. That is also using the concept of vector search. As you circle the object, it takes the object, it converts that into a vector and then does a vector search and goes and finds all objects which are similar to the reference vector and gives you the result. So vector search can be used in other scenarios also. But since we are in the OpenAI space, let me just show you what I can do with OpenAI. So now I am going to interact with OpenAI and I'm going to put in a query, which says type the name of a recipe, or I can ask it any question. So maybe it's a rainy day here. I want to drink something hot. So maybe let me ask, can I get So now if you see, it found out of the 13 ones that there are only 3 recipes that were similar to what I was asking for. So it took tiramisu, it took chai, and there was Irish tea. There were 3 things that it found similar, maybe because all of 3 had got milk in it. Now it sent those 3 documents to OpenAI. It sent my instructions, which is what I typed in earlier in my window, that I want something hot to drink, which has milk. and it generated this data based on what I had. So based on all the conditions that it should be hot, it should have milk, it found chai to be the similar. So it is not just giving you a recipe here. If I want to, I can ask. I can also ask a question like this. And again, if you see, it is now this time it found 3 different recipes, and then it generated a response which is appropriate to my question. So if you see that it's not just taking the recipe and dumping it. Every time I ask a question, it's doing something. Now, why is it giving me an ingredient? Why is it giving me step by step? I will show it to you because this is part of the prompt that I gave. I had told the bot that whenever you give a response, you have to give it in a format that the customer can see, cook it, and it should have the instructions in it. So now the other thing that I have done here is, for example, so here, when I said how to make pakoda, pakoda being Indian fritters, um, it says, sorry, I cannot provide instructions because it's not provided to you. So I also had provided instructions to the bot that you have to work within the data that I've provided you. You should not use your own recipes. So this is how you ground the response. You are trying to make sure that the responses are coming from your data and it is not using random data. So since let me just quickly show you how all these things were done in code. So here we have 2 services. One is the Cosmos DB service and one's the OpenAI service. So let me walk you through what is happening in each function. So one, the Cosmos DB service is very simple, where you're checking the collection exists or not. You are creating the Cosmos container. Remember, I said if the container doesn't exist, I can create it. So this is how, this is my vector policy. This is my indexing policy. This is what you saw on the UX also. So I'm creating my container through code. This is my query. So this, if you see here, I am doing a vector search. I'm doing a vector 3 and I'm saying, give me only the top 3 items. And that is why whenever I wrote a query, a natural language question, the system was giving me only top 3 search. So if I make this 5, then it will give me 5 items. But for me, I thought the system should check should pick from the top 3 items. So I put top 3 here. I'm writing a query to get the fields that I want to send to OpenAI, and I'm using similarity score to order it and then do a top 3. So this is my query where I send in a reference vector, and then I say, okay, I also say where similarity score is greater than this if I want to. So I'm saying I don't want to have anything which is less than, let's say, 0.5. So I only looking for qualified data. If there is a data which is very far from my reference vector, then I don't want to use that also. That's why I've given a similarity score as a minimum score for me to consider the data. And this is the one that is used to vectorize it. So it's basically select star from C. And these are some functions that are used to get the initial count, etc. This is the one where I'm doing an insert of the recipes. Again, it's a simple create insert item. I'm using bulk operations here. And here is when I complete my embedding, I do a patch, I do an update of my documents, I insert the vector with the values. So this is how I add vectors once the indexing is complete. So that's all I'm doing in Cosmos DB. So the most important thing, if you see, is this function on how I am using the vector distance function in Cosmos DB. Now coming to OpenAI service. First thing, I am generating my my prompt, system prompt. So this is what I was calling prompt engineering. Here I am giving instructions in native English to tell you how the system should behave. So if you see, the responses that the system was giving was all in alignment to this. So for example, if you remember, it gave you step-by-step instructions because I asked it to do If you're unsure of your recipe, you say you cannot, I'm not sure, ask us to search. If never refer to a recipe not provided as input. So all these instructions that I gave it in English, it is following this instruction and responding appropriately. Now, this is a iterative process. This doesn't happen the first time. You need to go through this multiple times to get this right. So you may have to try different instructions, most on the order of the instructions, the verbiage of the instructions, etc. So you will have to do some bit of trial and error here to get this right. I am connecting to OpenAI service, and I'm using the get embedding async function, and I am providing the deployment name, which is the model name, and I'm giving it the data that I want to embed. And in response, I get the embedding. So this is how you generate the embedding. And once I get the embedding, I send it to Cosmos DB to store it. Next is how do I get the response? So remember, I showed you that I send 3 pieces of information to the LLM. I send the system prompt, recipe assistant. This is the the prompt engineering instructions that we saw earlier. These are the JSON format, the serialized documents that were retrieved from Cosmos DB. And this is the native language input that the user provided. I send these 2 messages. One is called the system message and the user message. I provide these messages to the OpenAI completion model. And I call the get chat completion async function. And I pass these options to it. And what I get is the response, which you saw on the screen. So net, as long as you are able to generate proper prompts, you are able to retrieve the relevant documents, and you are able to provide the input that the user has provided in his native language to OpenAI, it will do its job and give you the response. Now, since in this whole space, Cosmos DB can only help you with the documents, the vector search functionality of Cosmos DB makes it a perfect choice for building OpenAI applications. So that's what I wanted to show.